Hello, this is Professor Matt Katroulis of Rio Hondo College, and this is the set of videos to accompany Experiment 6 on compounds and their bonds for Chemistry 110. This experiment covers many topics, and it largely is going to focus on ions and ionic compounds. So first of all, by looking at the formulas of the ions, naming the simple ionic compounds, looking at ions that have metals with variable charges, and then adding to that the compounds which have polyatomic ions. Then we will move to molecular compounds, which are compounds that can contain covalent bonds. And then finally we will look at electron dot formulas and shapes, also known as Lewis structures. So this experiment is yet another dry lab, meaning that we are not going to be using chemicals in this experiment. It's more like a homework assignment than anything else. And the homework assignment consists of two very large topics. The first topic is chemical compound naming, which we can otherwise call nomenclature, and that's parts A through E. And then Lewis structures and shapes, which doesn't get a huge amount of attention in this lab, but is a big topic in and of itself. You'll need to review your lecture notes and your textbook before you begin this experiment, because in order for me to completely cover these topics thoroughly, these videos would be 3 to 4 hours long, and I don't want that for this experiment. You can look at my video lectures when they're up to review those topics if you'd like, or just look at the ones that your instructor has provided. But what I will do is look at some of the most important ideas, discuss how to complete your lab report, and warn you about some traps that I don't want you to fall into. The most important topic to start off with before we approach this lab is the Octet Rule. Now, we have already seen in the lecture that with the exception of small atoms like hydrogen, lithium, beryllium, helium, what we find is that atoms follow the Octet Rule in forming their bonds. And the Octet Rule essentially tells us that atoms are most stable when they have 8 electrons in their valence shell. And why is that? Well, what elements have 8 electrons in their valence shell? It's the noble gases. And we know that the noble gases are the elements which are the least reactive. So in a way we could say that all the elements aspire to be like a noble gas, at least on the outside, in their valence shell. Now metals will usually lose all their valence electrons when they form compounds. And for now we're only going to deal with metals that form ionic compounds. So what that means is metals in group 1A, remember they have 1 valence electron, so they're going to lose that 1 electron. Now, they haven't lost any protons. You never lose protons in chemical reactions or exchanges, but you have 1 more proton than you do electron, so that means that these would have a 1 plus charge. The pattern continues in group 2A. They lose both of their valence electrons, and that leaves them with a 2 plus charge. The same is true of several elements in group 3A, but for right now we're just going to worry about aluminum. Gallium and indium won't play much of a role in this class, so we won't discuss them for now. But aluminum would lose its 3 valence electrons, and that would give it a 3 plus charge. What about nonmetals? Well, it depends on what nonmetals are going to combine with. If nonmetals combine with metals, then they're going to do the exact opposite of what metals did. Whereas metals lose valence electrons, nonmetals accept those electrons from the metals. And they want to gain enough electrons to get to having 8 electrons in their valence shell. So how is that going to work out? Well, elements that are in group 7A, the halogens, all have 7 valence electrons. That means their electron configurations are going to end in something S2, something P5, So they have 7 electrons. They want to get to p6. And so they're going to gain 1 electron. Now they have more electrons than they do protons, 1 more electron specifically, and that would give it a 1 minus charge. In group 6A, you have 6 valence electrons. So these elements are too short of having an octet. Specifically, again, 2 electrons short of having an octet. So they'll pick up 2 electrons from what they're reacting with, and that will give them a 2 minus charge. And then the nonmetals in group 5A have 5 valence electrons, and therefore they would gain 3 electrons. You want these to add up to 8. And so if you're picking up 3 electrons, that gives it a 3 minus charge. You'll notice I made a subtle change here. All of the elements in group 7A are nonmetals. In group 6A, most of those elements are nonmetals, and this only applies to the nonmetals. And the same thing with group 5A. This really is only going to apply, for example, to nitrogen, phosphorus, and sometimes arsenic. But arsenic is a metalloid, so we would be in a bit of a more complicated situation when we're talking about arsenic. Now, when nonmetals combine with nonmetals, what they do is they share electrons, and they achieve an octet through their covalent bonding. And we will talk about that in more detail when we get to part F. But for right now, we're just going to deal with the concept of ionic bonding. Your textbook on page 79, figure 3.2, has an excellent summary of these ions which only form 1 charge. So if we take a look here, the first thing I want to point out is the nonmetals. All of the nonmetals make a single charge that will never change. So if chloride is an ion, it's going to always be -1. When sulfur makes an ion, it's always going to be -2. Nitrogen, always -3. There'll never be an exception to that. You might ask about carbon, and carbon would be 4-, but we don't encounter that ion very often, and that's why it's been left out. As for the metals, as I said, all the group 1 metals form ions with a +1 charge. All the group 2 ions have a 2+ charge. Over in group 3A, aluminum has a 3+ charge. Gallium and indium below there probably do as well, but we won't worry about them. Now, what about all the blank spaces here and over here? Well, all of those metals can make more than 1 charge. Let me clarify. Most of those metals can make more than 1 charge, and we will talk about that issue coming up shortly. But for right now, make sure you have that memorized. Group 1A, +1. Group 2A, +2, etc. You need to know that information very well from looking at the periodic table. Electron dot symbols are diagrams which are designed to specifically call our attention to the valence electrons. What they are is the element's symbol surrounded by dots, where each dot stands for 1 valence electron. We can get up to a total of 8 valence electrons, but there are very specific rules as to how the first dots need to be placed. So the first dot can go above the symbol of the element, it can go below it, left, or to the right. So it doesn't matter so long as it's one of those. The second dot that you add can be in any of these positions, but you cannot pair it up with the first dot. So you could have a dot above and a dot below, or you could have a dot above and a dot to the right, just so long as they're not paired. When you get to 4 dots, it should make sense that the only way to do that is to have 1 dot above the symbol, 1 dot below, 1 to the left, and 1 to the right. When you go on to the next 4 dots, you have to start pairing them. But again, you can pair them in any order you wish. So for example, nitrogen has 5 valence electrons. So that means that there will be at least 1 electron above, below, left, and right. and then you have to pair one of those electrons with one more for a total of 5 dots. So let's take an example of this. So let's say we have boron. Boron is in group 3A. That means it has 3 valence electrons. And so there are many ways that you could do the electron dot symbol for it. So you could have a dot on the left, a dot above, a dot on the right. Notice that none of these dots are paired. Or you could take these dots like so and leave this side empty. All of these are fine, and they're all nice and clear, so long as there's no pairing. This would be an example of an unacceptable structure for boron, because they've paired the electrons rather than separating them out. If we look at argon, argon has 8 valence electrons, so this is showing a complete picture of what it would look like when all 8 electrons are in place. If we'd like to figure out the electron configuration of an ion, what we want to do is to start out with the original neutral atom as our starting point, and then we will adjust the electrons accordingly. For a cation, that is a positively charged ion, we're going to just take away all of the valence electrons. Those will usually be the electrons in the outermost S subshell and any electrons that would be in the P subshell as well. So let's take a look at magnesium. Magnesium's electron configuration is given right here, and the valence shell would be the third shell. It's got 2 valence electrons. So magnesium is going to lose all its valence electrons. And that will leave this as the electron configuration for the magnesium ion. Notice how losing 2 electrons gives you 8 electrons in the valence shell, because now the valence shell is no longer the third shell, it's the second shell, and the second shell has 8 electrons. So that's how a metal gets to an octet, losing those valence electrons, leaving a new outer valence shell. When cations only form one charge, the name of that ion is just going to be the same as the name of the element. So, for example, this is just the magnesium ion. For anions, the negatively charged ions, we still start out with the electron configuration of the neutral atom, and then we add electrons to the last subshell. And this is always going to be a P subshell. Let's look here at sulfur. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So it has 2 plus 4, or 6 valence electrons. Sulfur is in group 6, and we already saw that that means it wants to gain 2 valence electrons to get to 8. And so those 2 valence electrons will go into the last subshell, 3p, and so that leaves us with 3s2, 3p6, 8 electrons, or an octet in the valence shell. And this is now our new ion. Now, its name is going to be a little bit different. For anions, what we do is we take the first syllable of the element and then add the suffix "ide." So sulfur would become sulfide. So, for part A, what you want to do is just complete the table at the top of page 69 using the example that they've given here. You'll want to make sure that you mark your dots as cleanly as you possibly can. For column 3, where it talks about loss or gain of electrons, you need 2 pieces of information, so either the word gain or lose here, and then how many electrons. This E- is just the symbol for an electron. You'll notice that the electron configuration should always have an octet. So 2s2, 2p6, that is 8 electrons at the end there. And then we write our charge, the symbol of the ion, and this is the sodium ion, so it's sufficient just to say sodium. Be sure and be careful when you have an anion, a negative ion, it's ending changes to "ide." So just like we saw a moment ago, sulfide. You can go ahead and pause the video now and complete Part A. When you're ready, unpause the video and we will continue with the next topic. Now that we've had a chance to look at ions, let's take a look at the compounds which they form. So I'd like to review 4 very important rules when we are drawing the formulas of ionic compounds and looking at naming them. The first and probably most important rule is that the total charge of all ions in a compound must add up to 0. So that means we're going to add cations, which are positively charged, with anions, which are negatively charged, and they must ultimately add up to 0 in the formula. The cation is always written before the anion. So in almost all cases, that will be a metal before a nonmetal. The only exception to that we'll see is when we get into polyatomic ions, and even then, only one polyatomic ion is a cation, ammonium. The subscripts that you see in the formulas have to be in the lowest whole number ratio. And you don't write any charges at all in the final formula. When you're writing out your work, you might want to write in charges, but the final formula is not allowed to have any charges at all in it. So let's look at barium sulfide. Barium is in group 2, so that means it will form a 2+ ion. Sulfide, as we just saw a moment ago, sulfur is in group 6, and that means it will need to gain 2 electrons, so that would be 2-. One of the common ways to write formulas is just to switch these numbers right here. So we might say Ba2 and then S2, and that might be one way to do it. But which of these is the correct formula? Well, remember we said on the rule, the third rule up here, we must write these formulas in the lowest whole number ratio. So 2 and 2 are both divisible by 2. So we divide both of these by 2 to get it down to a 1-to-1 ratio. So in Part B, when you're asked to determine the physical properties of the compounds in parts B, C, D, and E, it's sufficient to just look up the compound on Wikipedia. And you will usually see the picture off to the upper right part of the web page, and then as you scroll down you'll see the properties on the right side in tables. You must report the density values in either grams per milliliter or grams per cubic centimeter. If you are given, for example, the values of kilogram per meter cubed, you want to avoid those density values. That's not what you want. You want to look them up in these units here. The melting points you look up need to be in degrees Celsius. If you can only find them in degrees Kelvin or Fahrenheit, then you need to convert them using a unit conversion. And don't forget, you need to write the units on the report sheet in the boxes where you're asked for these properties. So for Part B, you want to complete the 2 tables at the bottom of page 69 and the top of page 70. And double check that every formula that you write followed the 4 rules that we saw on the previous slide. That the total charges add up to 0, that the cation is always written before the anion, that the formulas are written with the elements in the lowest whole number ratio, and that there are no charges written in the final formula. And you should note that all of these compounds are going to end in "ide." Now, we haven't talked yet about nitrate or sulfate, so if you find yourself writing something that ends in ate or ite or any of these things like that, you must have made a mistake. We haven't talked about how to approach those compounds yet. So you can go ahead and pause the video, and when you're ready, go ahead and unpause it, and I will continue on to the next topic, which has to do with ionic compounds. Continuing on. There are a few other metals which also make constant charge ions, so in addition to group 1 and group 2 and group 3. And these three are going to be the silver ion, which always has a +1 charge, the zinc ion, which is zinc with a 2+ charge, and the cadmium ion, which has a 2+ charge as well. So this is going to bring up a very special little group. The ions from group 1A always have a 1+ charge. The ones from 2A always have a 2+ charge. Aluminum always has a 3+ charge. And as far as we're concerned, the three ions above always have constant charge. So I will always call these the constant charge ions, all of these guys right here. Every other metal will not be a constant charge ion. They will form a variable charge ion, meaning that they can have more than one possible charge. And so that's the case for many, many elements, like, for example, iron, lead, tin, and many, many others. So let's take a look, for example, at iron. Iron very commonly forms this ion and this ion, and sometimes it has a 4+ charge, although we're not going to ever encounter that. And copper will form an ion with a +1 charge, and it forms an ion with a 2+ charge. Now, this means we're going to have a problem, because all of these ions, for example, could combine with chloride. And so the first iron ion with 2+ charge would make this compound, and this ion here would make the compound with 3 chlorides. Why 2 and 3? Don't forget, Rule 1 says that the total charges must add up to 0. So if this iron has a 2+ charge, chloride always has a -1 charge. We would need 2 of them to cancel out the 2+ charge. So we can't name both of them iron chloride because we wouldn't know which one we're talking about. And in fact, they have different properties. So in these types of compounds, we include the charge in the name of the cation. And the way we do that is we determine the charge, and then we attach it to the name of the element in parentheses, and then write that number in Roman numerals. So this is called, if I'm reading it, the iron 2 ion, not the iron II ion, the iron 2 ion. And this is called the iron 3 ion. If you're not too good with writing Roman numerals, you'll want to review how to write them up to 4. So the name of this compound then is iron 2 chloride, and this compound right here is iron 3 chloride. Be sure you do not make the mistake of looking at the number right after iron and assuming that's the charge. Some people might go, oh, this is iron 1, because there's no number there. Okay? You have to figure that out, as you're going to see now from the anion. Now, the Roman numerals only appear in the names of compounds which have metals with variable charge. So all the elements you just saw a moment ago, like sodium in group 1, magnesium in group 2, or silver, zinc, and cadmium, which have constant charge, we don't write Roman numerals for those ions. So what are the formulas of tin 2-bromide and lead 4 oxide? Well, this is telling us we have tin with a 2+ charge. Bromine in group 7 will make a bromide ion which has a 1- charge. So if tin is 2+ and bromide is -1, I need 2 bromides to cancel out the positive charge of the tin. So SN2 plus is combining with Br minus. This is the final formula. Notice that the charges are not written in the final formula. What about lead 4 oxide? This is lead with a 4 plus charge. Oxygen is in group 6A. You should be checking this with the periodic table as I go. So it will make a 2 minus charge. So if this is 4 plus, this is 2 minus. I need 2 times 2 minus. That would be negative 4 to cancel out the positive 4 charge. So this should be written as PbO2. These are, you'll notice, in the lowest whole number ratios. Let's try some compounds that are a little bit more challenging. So what is the name of this compound here and this compound here? Well, both of them have something in common. They both begin with an element of variable charge, and we have to figure out what the charge is before we can name the compound. So how do we do that? We need to remember the total charge of the compound must add up to 0, and very important, the charge of the anions never varies. It never changes. So by looking at the anion, we can always figure out the charge of the cation. So this is our logic here. Chloride in group 7 is always negative 1. There are 3 chlorides, so that means we have a total negative charge of negative 3. This means that the total positive must be positive 3 so that we can cancel out the negative 3. Remember, they have to add up to 0. How many cobalts are there? There's only 1. So it must be a positive 3 charged ion. So this is cobalt 3 with the chlorides, and so the name is cobalt 3 chloride. B might be a little bit trickier. Well, we start off with the oxygen. Oxygen always has a negative 2 charge. So we have 3 of them, so 3 times negative 2 would be a negative 6 charge. So the 2 chromiums are going to have the same charge that adds up to positive 6. So how do we get that? Well, positive 6 divided by 2, each one of them must be positive 3. So we've got 2 chromiums, which are each positive 3, that's positive 6. 3 oxides, which are negative 2, that's negative 6. So everything here adds up to 0. So the name of this compound is chromium 3 oxide. Now I will admit these are common sources of mistakes, and you want to be very, very careful when writing names with compounds that have ions with variable charge. For part C, you're going to essentially follow the same instructions as for part B. So this first part here is exactly the same as what I said. You look up the compound. When you're doing physical properties, look up the compound on Wikipedia. Again, the pictures are there. The densities have to be given in the units specified here. Melting point must be in degrees Celsius, and then convert to those units if you need to. And be sure to write the units out on the report sheet. Do not look up the names or the formulas on Wikipedia, because sometimes people do make mistakes doing that. So you'll want to complete the 2 tables on page 70. Again, make sure that all of these formulas follow the 4 rules that I mentioned earlier for all ionic compounds. Part C is still about ionic compounds. And all of the names that you write on page 70 will end in IDE, because we still haven't talked about ions that end in ate or ite, and that will be coming up next. So I'm going to go ahead and end this video here, And when you're done with part C and you're ready to continue with part D, go ahead and go on to the next video. Thank you.